In 2013, Boeing launched the 7X as a bold leap forward, a twin-engine jet designed to carry nearly 380 level passengers while burning fuel like nothing before it. With a massive composite wing, folding wingtips never seen in commercial aviation, and the largest turbofan engine ever built, it promised to redefine long-haul travel and set a new efficiency benchmark. But everything depended on one machine, the GE9X, marketed as the most advanced and fuel-efficient engine in GE's history. It was the heart of the aircraft's performance claims: record thrust, higher compression, lower emissions. If it worked, the 7X would change aviation economics. If it didn't, the entire program would unravel. By 2018, cracks began to show. High-pressure compressor durability problems delayed the first flight. Critical components deteriorated faster than expected, forcing redesigns before the aircraft even left the ground. Certifications slipped. The timeline moved. Engineers insisted the issues were fixed. And in January 2020, the 7X finally flew. But certification didn't end the trouble. In 2022, a temperature alert during testing revealed combustor liner problems. Flight testing paused again. Emirates publicly questioned whether the issue was isolated or something deeper in the engine's design. Each new problem triggered more scrutiny from regulators. Still wary after past certification failures, confidence started to thin. Then came August 2024. After a routine test flight, inspectors discovered a severed thrust link, a structural titanium component connecting engine to wing. Further inspections revealed cracks across the fleet. The entire 7X test program was grounded for 4 months. This wasn't a software patch or a minor tuning issue. It required a redesign of a load-bearing structure. The financial consequences followed quickly. A $4.9 billion charge tied directly to delays. Over $15 billion in total program charges. The aircraft, once expected in service by 2020, now targeted for 2027, a 7-year delay. Boeing acknowledged it may not recover development costs on the first 500 aircraft. Meanwhile, 27 jets have already been built. Most sit in storage, waiting for certification that keeps moving further away. Airlines have reworked fleet plans. Older aircraft stay in service longer than expected. And although the GE9X received FAA certification in 2020, post-certification issues continued to surface during flight testing. The 7X still promises unmatched efficiency and capacity. Orders remain strong from major carriers. On paper, it bridges a gap no other aircraft fills. But after years of delays, redesigns, and mounting costs, one question hangs over the program. Will the engine that was meant to secure Boeing's future ultimately prove to be its greatest vulnerability? But to understand why this engine matters so much, you have to zoom out, because the 7X was never just another aeroplane. For decades, long-haul aviation followed a pattern. Bigger aircraft meant for engines, more fuel, higher operating costs. The Airbus A380 proved that scale alone wasn't enough. Airlines loved the capacity. They struggled with the economics. Airports weren't built for it. Routes couldn't always fill it. Boeing saw that gap. Instead of building something bigger, they tried building something smarter. A longer wing made from carbon fiber composites. A 235-foot span that folds at the tips so it can still use standard gates. A cabin redesigned for 18-inch economy seats. And at the center of it all, the GE9X. The math was simple. 2 engines instead of 4. Near A380 capacity. Double-digit fuel burn improvements. Per seat costs down by around 20% compared to older 777 models. If it worked, airlines wouldn't need super Dumbos anymore. But this is where the story starts to get uncomfortable. Because the GE9X wasn't just slightly better than its predecessor, it was radically different. A 134-inch fan, 16 composite blades instead of 22, a pressure ratio of 61:1. Far beyond what the previous GE Aerospace engines achieved. More heat, more compression, more stress inside the core dot, and higher stress means tighter tolerances, smaller margins. When engineers found high-pressure compressor components degrading early, it wasn't a cosmetic issue. It hinted at something deeper. How far could they push performance before reliability pushed back? The fix came. Certification followed in September 2020. On paper, the engine passed. But certification doesn't mean the story is over. It means the old testing begins. By 2022, Temperature alerts appeared in a high-time test engine. A combustor liner issue forced another pause. Inspections expanded. Regulators asked harder questions. After the 737 MAX crisis, the Federal Aviation Administration wasn't going to move quickly. Every anomaly now triggered broader reviews, more data, more validation, and time started becoming the most expensive component on the airplane. Airlines like Emirates had built long-haul strategies around this jet. They ordered more than 200 of them. Qatar Airways placed massive commitments. Lufthansa prepared to be first in line for delivery. Each delay wasn't just inconvenient. It reshaped fleet planning, routes, crew training, capital budgets. And then came the thrust link discovery in 22.4. It didn't originate inside the engine core. It wasn't a combustor or compressor issue. It was the physical connection between engine and wing. Titanium links designed for redundancy cracked across multiple test aircraft. The vibration that caused it wasn't initially predicted at that level. Engineers redesigned the component. Temporary fixes went in. Ground tests expanded. But something subtle had shifted. Until that moment, most issues lived inside the engine. Complex, difficult, but contained. Now the problem crossed the boundary between engine and airframe, which raises a quiet question no one likes to ask out loud. When you design the most powerful commercial engine ever built, are you also redesigning every structure around it? Because more thrust means more loads. More loads mean new vibration profiles. And new vibration profiles reveal weaknesses that didn't exist before. That's not failure. That's frontier engineering. But frontier engineering is expensive. By late 2025, Boeing had taken over $15 billion in charges on the 7X program. The company admitted it would not recover development costs across the first 500 aircraft, a position known as reach forward loss. 22 completed jets sit, parked, painted, finished, waiting. From a distance, they look ready for passengers. Up close, they're symbols of something else. How difficult it is to compress the future into a schedule. And here's the part that rarely gets said. Despite everything, the underlying performance numbers still hold. The wing still delivers aerodynamic gains. The cabin is genuinely more comfortable. The engine, when running within updated parameters, still achieves remarkable efficiency. The question isn't whether the 7X can fly. It already has more than 1,000 times in testing. The real question is whether aviation's new philosophy, extreme efficiency through extreme engineering, comes with trade-offs we're only beginning to understand. Because the 7X represents a shift from incremental improvement to pushing the edge, and history shows that when aerospace pushes the edge, the first chapter is rarely smooth. So when this aircraft finally enters service in 2027, it won't just represent a new jet. It will represent something else entirely, a test of whether modern aviation can balance innovation, certification, and financial reality all at once. The engine that was supposed to guarantee dominance has already rewritten timelines, balance sheets, and expectations. And maybe that's the real story. Not whether the GE9X succeeds, but whether the industry can afford to keep building aircraft that only work if everything works perfectly. Because if this is the new model for progress, what happens the next time an engine gets even bigger? And that question doesn't just belong to Boeing, that belongs to the entire industry. Because the 7X isn't an isolated experiment. It's a signal. For decades, aircraft development followed a rhythm. Improve the wing a little, refine the engine, reduce fuel burn by a few percent, certify, deliver, repeat. The 7X broke that rhythm. It stacked innovation on top of innovation. A composite wing this large had never been built for a widebody in this category. Folding wingtips had never been certified for a commercial jet of this scale. And the GE9X pushed thermal and pressure boundaries beyond anything that had flown passengers before. Each individual step was achievable. Together, they created a new level of complexity, and complexity changes risk, not dramatic, headline-grabbing risk, but layered risk. When the high-pressure compressor ran hotter than expected, engineers corrected it. When combustor liners showed temperature concerns, they redesigned them. When thrust links cracked, they strengthened the structure. Each FIX made the airplane stronger, but each fix also added time, and time is what transformed a promising program into a financial burden. Here's what makes this especially difficult. None of these problems were catastrophic failures. There were no accidents, no emergency landings in service, no public crisis. This was engineering catching issues before passengers ever stepped on board. From a safety standpoint, that's exactly how the system is supposed to work. But from a business standpoint, catching issues early doesn't make them cheap, because airlines don't measure innovation in engineering milestones. They measure it in aircraft delivered. Every month the 7X remains in testing is another month older. 777 to 300 ERS stay in service. Another month, airlines postpone route expansions. Another month, billions of dollars sit idle in completed aircraft, waiting for approval.